Introducing THETA, thermochemical energy for tough applications.
Sand manufacturing is one of the most energy-intensive industrial processes. As steel billets cool down, they radiate their heat to the environment, effectively losing it forever. However, the Oregon State Thermochemical Energy Storage Lab has created a novel solution to help trap, store, and reuse this energy.
What is the current state of the steel manufacturing industry? China now accounts for over half of global steel production.
In order for American companies to compete with Chinese competition, it is critical that we invest in new infrastructure to help make the process more efficient.
Our lab has partnered with the Oregon State Advantage Accelerator, a program that helps business startups connect with industry leaders.
Through this program, we learned that competition in the field of thermochemical energy storage is almost non-existent. Therefore, only a successful pilot is required to bring our product to market.
How does thermochemical energy storage work? Certain materials, including copper oxide, are known to decompose under high temperatures, absorbing energy to release oxygen. This effectively stores the heat energy as chemical potential. You can then float oxygen to perform the reverse reaction, which releases the heat energy when you need it. Let's take a look at Johnson Hall, where we house one of our reactors.
So here we have the reduction reactor, or the charging step, and the particles move through this reduction reactor and then they get collected at the bottom in this collection tank. And then when we want to do the reverse step, we load them in the back where we have the oxidation reactor. And then when they oxidize, they release all that heat.
Why is thermochemical energy storage the best solution?
So thermochemical energy storage has the advantage of higher energy densities over, say, sensible or latent energy storage. So since it has higher energy densities, you can have more energy stored in a smaller volume, and generally smaller volumes correlate with lower costs.
By using the discharge reaction to bring air up to 900 degrees Celsius, we can make heating up the next round of billets more efficient. Our modeling has revealed a 37% reduction in methane consumption through our process.
What is our past experience and future work plans?
So we've been working on thermochemical energy storage for the last decade. We generally work on applications of high temperature heat to chemical potential. I see our lab developing pilot scale reactors. We've developed kilowatt scale reactors, and we're going to be scaling that up.
We are in a good path to scale this system to approximately 5 to 10 times. We will be able to do something at a commercial or industrial scale in the next years.
As long as funding supports local projects, engineers can develop innovative solutions, improve energy efficiencies, and contribute to economic outputs. Thank you for watching.